Thank you to all the participants who have joined and who have just joined in. Thank you for joining ATDI's fifth official workshop. Today's workshop will be on how to unleash the power of drone-based antenna measurements. This will include demonstrations on the methodology for techniques in predictive modeling and how to verify these models. My name is John. I'll be moderating. Everyone will be left on mute. Please raise your hand or use the Q&A function in the toolbar if you have any concerns or have any questions. I'll answer what I can. Otherwise, the questions will be held onto at the end during the Q&A session.
Good morning, everyone. This is workshop number 5, ABU DBS for 2023. My name is Yaya. So we have two presenters co-presenting, Yaya and Jason. So we'll be introducing ourselves later on. So with two different companies coming together to show you how these two companies come together to deliver a solution for broadcasting. So the title of the workshop is Unleashing the Power of Drone-based Antenna Measurements. So it's about using drones for antenna measurements and then using these measurements to do predictive coverage modeling. So first, the agenda. So guys, this is designed to go in 6 different parts or 6 different sessions. So number 1, we will do the introduction. So I'm going to introduce myself, my company, and then Jason will jump in and then also introduce himself and his company. And after that, we will move on to 2 different two sessions. Jason will be talking about the use of drones for doing the measurements, the collection of the measurements, flying, and then producing a model, antenna model, radiation pattern. And then we'll move on to ATDI. ATDI will be doing the verifications, updating the model, and then using this information for coverage planning. So each one of us will spend about 25 minutes. Then we move on, and then in the end, we'll do the drone-based coverage measurements for 10 minutes, and then ATDI will conclude with the model tuning, calibration, and so on. And you get to ask questions in the end. So a little bit of introduction about ATDI. ATDI is a French company, headquartered based in Paris, and the regional office in Sydney. So Sydney is looking after the South Asia Pacific region. And we've been in the industry for more than 30 years, and we've been in Australia for more than 15 years. And we're looking after, we provide solutions in radio network planning, because we develop, maintain, support RF planning tool for radio network planning. And we also do spectrum management, digital cartography. We supply maps, high resolution maps, medium resolution maps, which you need for RF planning. We also provide professional consultation services and training. And our tool cover a number of verticals. So we do broadcasting technologies like AM, FM, ISDB, ISDBT, DVB, DRM. We do all this kind of broadcasting technologies, ground wave, sky wave, regardless what frequency you operate in. We also do point-to-point microwave link planning, modeling, simulations, which you need for backhauling for these broadcasting towers. We are also in the land mobile radio domain, like public safety, oil and gas. We also in the mobile technologies, 2G, 3G, 4G, defense, electronic warfare, jamming, interception, IoT, interference, coordinations, you name it. Okay, so we have a comprehensive solution covering the needs of all RF-related industries. So I'll pass the presentation now to Jason.
Good morning, everyone. Thanks for all those live audiences, and thanks for everyone in the webinar. My name is Jason Schreiber. Thanks for the intro, Yaya. John, just want to make sure, is everything good at the moment?
Yep, I can hear you. You want to intro yourself with the video, and then just to be able to cut with the lagging, you want to turn the video off.
Okay.
After you've done your intros. Yeah. Yes, the video is on at the moment.
Okay. Okay, so let me flick this.
But the sharing is working. Yep.
So just going to technical complexity here. Okay, thanks for that. A little bit about Sixarms. I'm Jason Schreiber. I'm the Managing Director for Sixarms. Sixarms is actually a very niche little company based in Australia. We're an RF consultancy company founded back in 2015, basically out of the need for better testing and commissioning tools for broadcasters, and mainly in the coverage validation and antenna verification space. We make use of lightweight receivers, capable airborne platforms, that basically means drones, and heavily rely on automation to solve some broadcast coverage issues and antenna pattern issues. And we do that in a more timely, efficient, and accurate way than previously done before. But there's a list of clients there that we've got, and they're also defense clients, government clients, broadcasting clients. Personally, myself, I'm passionate about making complex problems simple, automating routine tasks, and using technology to generally make life for myself and others more rewarding. Got about 25 years in the industry, been lucky enough to be employed as in a government regulator position, broadcast and defense infrastructure, cellular operator, and throughout the world as well, South Africa, UK, USA, Australia, New Zealand. And right now I'm the founding director of Sixarms, and I run that. So ATDI and Sixarms, why would we collaborate on this workshop? Well, it's actually a really good fit. What Sixarms does is we measure antenna patterns, and what ATDI do very well is they use those antenna patterns to be able to create a really good coverage prediction of what your broadcast signal is doing. Sixarms can measure these signals. We measure them close to the site, so we actually test the antenna system that's transmitting the signal, and we can also measure it in the coverage area as well. ATDI can then use those measurements to improve their coverage modeling. Okay, just a couple of steps backwards. Broadcast antennas, they come in different shapes and sizes. They are not all equal. I've got a couple of pictures here of some different types. We've got some panel antennas, panel UHF, DVB, DTV, ATSC antennas. We've got some panel FM, HD radio antennas. We do AM, DRM radio as well, DAB+. It doesn't matter the technology, the ultimate solution is very, very similar. The point is that all of these antennas are designed for a specific purpose, right? They're designed to meet your operational coverage measurements, your needs, and they're also designed from a regulatory point of view that they do not interfere with anybody else. So for compliancy. So let's take another step backwards about antenna patterns. So an antenna, we just saw the physical antenna, what it looked like. It's actually defined by its electrical characteristics. So where does that signal radiate? And generally when you purchase an antenna from any one of the manufacturers, they'll give you a specification sheet. On that specification sheet, it will tell you where the signal is going and how much is going where it's going. We basically break those down into two components. We call them an azimuth pattern. So if you had to chop the antenna in half, looking down on it, that shows you where your signal is going in a 360-degree space. Is it pointing east? Is it pointing west? And then we can also do what we call an elevation slice. So elevation slice is if you had to basically go from the ground all the way up to the antenna. It's showing you where the radiation is going in that direction. So is your antenna pointing up towards the sky? Are you aiming for the sky? Is your antenna pointing down towards the town, the population that you're trying to cover? That's your elevation pattern. And then the third characteristic they give you is a radiated power, effective radiated power. So that's how much power you're allowed to emit in any direction. So those kind of plots, the azimuth plot and the elevation plot, that's what we use to determine really whether an antenna is operating as it should or if it's faulty. Now, if you can look at these plots, I'll try and get the laser pointer out. Generally, your plot is either linear or logarithmic. It depends on what the antenna manufacturer gives you. But for all the plots that I'm going to show you in this presentation, they're all real. These are all measured. There's no theoretical here. The theoretical is normally the red plot, the dashed line in the back, right? So that dashed line is what the antenna manufacturer says. That's what you should have. And then normally the black measurement on top of that is what we have actually measured with our drone-based RF measurement system. And if they agree, that's perfect. And if they don't, well, we need to know why they don't agree. What are the traditional ways that we used to do this? Well, we used to drive around in a vehicle with a pump-up mast, portable mast. We used to go up 10 meters. And as we go up in height, we used to measure the layering profile, basically the multipath from 0 to 10 meters. And that was the RTU standard. The FCC calls for 9 meters. So can you accurately tell whether your antenna is working properly from a spot measurement with a vehicle? The answer is probably not, no. The uncertainty is just too great. And for you to do 360-degree points around a tower would probably take a couple of weeks. So they're difficult to, it's time consuming, you're limited to 10 meters, you're affected by multipath. Okay, so what's the next step? Well, we can put the antenna on a helicopter. We can go around and measure our antenna patterns with a helicopter. And sure, that's what we did, because that was the technology available at the time. However, as soon as you jump into a helicopter, you're now putting person and people at risk. You're also now dealing with FAA and aviation regulations, and they don't generally like antennas hanging off helicopters. So the solution is, because the technology is there, is a drone-based RF measurement system. So it's automated, there's less risk to any human life. The data is live, you can get into a free space condition, and the scalability is there, and the cost is lower. All right, so why is it important? Why do we need to measure an antenna pattern? Why do we care? Well, this is just one little example I'm going to show you where the antenna manufacturer, a really reputable USA manufacturer, gave us the antenna pattern, which is the red one. And that's what you'd expect to be getting. So that red antenna pattern is, it's a slot antenna, UHF TV. Its designed radiated power is about 371 kilowatts. Perfect. If you wanted to stop there, you could. You could take that design pattern and throw it into ATDI's coverage prediction software and get a beautiful coverage map, right? Without even thinking any further. But here's the problem. When we went to go measure that antenna with our system, we actually measured that black antenna pattern. So that black antenna pattern, obviously the shape is quite different to what you would expect. The radiated power is a lot lower than what you think it would be. And what does that mean? What does that mean to you as the broadcaster or the person who's relying on that signal? Well, here's just a short example. Here's a short example what it does mean. If you now, I know these plots are not the best for you to see anything, but the main thing to take away is if you put that theoretical manufacturer specification into your coverage prediction software, you're going to get a beautiful number, right? We're going to get 385,000 people. That's how many people we're covering with that antenna. But in reality, they are not covering that amount of people. We now have the measured antenna pattern. So the point here is that we're now, with our measured antenna pattern in the prediction software, we're now getting 350,000 people. We've now lost 30,000 potential viewers, potential listeners. Your bottom line, your revenue has just decreased by knowing exactly what your measured antenna pattern is. The good news is that you can go and fix that antenna pattern and you can push it back up to the 385,000 people that you were supposed to measure. So why is that still important? Well, let's look at it from a regulatory compliancy point of view. Regulators have filed license applications with theoretical antenna patterns and maximum radiated power requirements, which they use to calculate interference and for engineering purposes. The regulator relies on the licensed information that you supply them, so those theoretical patterns, right, to do all the calculations. So what does it mean in this example when the licensed theoretical pattern from the manufacturer is the red one? Because that's what the regulator thinks that you're transmitting. But once you've measured that antenna pattern, the real one is actually the black one, and it's out of alignment. So there's an installation issue clearly with that antenna. So what does that mean to you as a regulator? As an operator, it may not mean anything because you may not be worried that it's pointing in the wrong direction. But for all your interference calculations and everything like that, you may want to actually know what those antennas are doing as opposed to relying on manufacturer theoretical data. And just to bring home that point again, broadcast antennas are carefully designed to radiate certain directions with a certain power. They're designed like this because we're trying to hit a certain coverage, we're trying to hit a certain population. So if you choose a little peanut-shaped antenna pointing in a certain direction with 250 kilowatts of radiated power, you'd hope that when that antenna is installed, you're getting 250 kilowatts radiated power. But what we're finding is that that's not always the case. Unfortunately, there are too many installation manufacturer defects happening with installed antennas that cost a lot of money, and there is no verification program in place. So in this particular case, we've got a little peanut-shaped antenna. You can see by the red that it's installed significantly wrong between the black and the red, so slightly offset azimuth. The good news is once they measured that, they fixed it, and we remeasured it, and it lined up perfectly. So the broadcaster is now happy. Okay, 3 main reasons for causing all these problems, the difference between the manufacturer data and the measured data. What are they? Well, the main one is installation error. So offset rotation. So if you're looking to mount an antenna on top of a structure, you've got 12 holes. The guys have installed the hole one to the left, or they've installed it one to the right. And so that first picture there shows you an offset of the mounting system. The second middle picture shows you a bit of a phasing issue between panels of a paneled antenna. And the third one is terrible, it's horrendous. So unless you are shooting your signal up to the moon, 0 degrees is the horizon line, and this antenna is pointing way above the horizon line, which means if you had a dual feed system going to your antenna system, the phasing between the 2 main feed systems is what causes your beam tilt. So this antenna is pointing up, it's intended to be pointing down. Manufacturer errors. Now these are a little bit easier to spot because the shape of the antenna is a lot different to what you think it would be. So in particular, that middle pattern there, the red is what the manufacturer says you should be getting. The black is what we measured. The fact that there are 2 black measured lines there just means that we've measured that antenna over a span of 2 years and came up with the same measurement as we were, trying to argue our case with the antenna manufacturer. The third one is a phasing difference between a 5-paneled antenna and the phasing between the faces. So between face A, B, C, D, and E is incorrect and out of alignment. So significant differences between what you think you have and what you actually have. Local and structural effects. So this is something which is a little bit more complex to try and deal with. So if you're installing an antenna and you've got multiple other antennas close by, in close proximity, you're on a tower, an antenna farm, maybe there's other towers next to your tower. What will happen is that you could get a notch in your pattern, and that notch is shown in the first slide, the northern and southern end. You've got 2 towers which are actually very close proximity to that antenna pattern, and they're actually affecting your pattern in that direction by a couple of dB, even half power. May not be significant, but it may be if the managing director of the company is living in that area. The middle one. Now this is the client asked for an omnidirectional antenna, and the specification they got was the nice red, reasonably omnidirectional antenna. The problem was that they installed that antenna on a side mount of a structure. So the omnidirectional is not omnidirectional anymore. Any antenna that's side mounted on a structure interacts with it. If it does not have reasonably good shielding or reflector, it's going to interact with that structure significantly, and you cannot predict this. There's no model that you can, electromagnetic tool that you can use to predict that middle pattern. They get close, but the problem is every input that you put into that electromagnetic, that modeling tool needs to be 100% correct. So the easiest way is to just take half an hour and go and measure the thing. And you have significant nulls and peaks due to interaction with the local steelwork. The third one is very similar. It's a side mount antenna. And that could be significant. The southern lobe there could be, from a compliancy point of view, very important because it's now interfering into an adjacent channel or a co-channel that's a couple of 100 kilometers away or something. Look, it's not all doom and gloom. When we measure antenna patterns, generally this is what we get. The theoretical and the measured line up pretty damn well. Radiated power measures up pretty well. When we do spot a mistake, it usually is because there's an installation or a manufacturer issue. Okay, so what do we need to be able to kind of employ a drone-based antenna pattern program, right? Well, we need 3 components. We need to understand the process. Okay, that's well documented already. Go to the ITU recommendations, they tell you what to do there. We need equipment. We need a drone. We need some sort of receiver. We need antennas. We need mounts. We need, and this is the most important bit, we need a bit of software that can bring it all together and make sense out of what all these inputs are. And this is what Sixarms does. We make sense out of all those inputs and we present it in a way that's meaningful. All right, so we need a drone. Okay, what kind of drone can we use? Well, we used to have to make our own, but thank goodness we don't need to do that now. We can use a standard off-the-shelf drone, which means you in your local country can purchase a drone from your local manufacturer and have that relationship with them. What Sixarms will provide is the arms receiver, the mounting system, and all those little lightweight PCB and metallic antennas for different frequencies. So you could have AM radio, FM radio, UHF, cellular. That's the equipment that's needed. And then finally, to bind it all together, we need some sort of application, right? We need a field app, some sort of software that allows planning, allows data processing, visualization, automated reporting, and it allows the flight plan creation for the drone. So where the drone flies is heavily constructed by the software and the inputs of that antenna, whether it's a panel antenna, whether it's a large antenna, whether it's a smaller antenna. All of that gets taken into consideration from our software, and out comes a flight plan for you to put into the drone. So this next slide is a little bit of a video of a real measurement, but we've just reconstructed in a 3D format just so that you can have a look at it. And it'll go through, it's about 2 minutes long, it'll go through the process of measuring an antenna pattern and the visualizations that you'll get from our system. So let's see, play on that one. Okay, the drone's taken off. We're at the tower. The tower is the green section. The drone is now flying out to do an elevation pattern. It's hit a certain distance and it's flying straight up. It's then measured the peak and now it's moving to the next elevation slice. So this antenna is a 4-faced panel UHF antenna. We're doing all 4 elevations in one flight. The distance from the antenna to the drone is around about 600 meters or so. And that's defined by the far field, which is based on the frequency and the size of that antenna. So this is sped up, I think, 20 times. So that's not real time, obviously. So that's the flight path the drone does to get all the elevation patterns. Then as the drone lands, the operator, while the drone is in the air, this is what the operator is seeing live. So the drone's flying in the air. It's red because it's getting to its start point. When it gets to the start point, it automatically knows where it is and it starts capturing that data. And so we got all the lobes of the elevation pattern. And there we've just hit the peak. So we know where the beam tilt is of that antenna. And it'll do that for the 4 elevations. So that's live. That's while the drone is in the air, you see that data. We then move on and we do a azimuth slice or an azimuth flight. And you try and do that at the peak beam of that measured elevation pattern. So it flies out and it does a perfect 600-meter circle at the correct depression angle for that elevation. And there's just no way that a helicopter pilot can, fly as accurately as the drone flight controllers these days. And then as the drone finishes its orbit, it'll land and we'll just get a screenshot of the video of which what the controller is doing. So first of all, this is just a video of a little GoPro camera on the drone, just so you can see that's its orbit. That's the distance away from the antenna. None of those antennas are the receive antenna for the broadcast signal. That's just your telemetry signals. Then the software will show you live once again. We turn our drone into an F-16 fighter pilot, but as the signal goes across around the antenna, this is what you're seeing live. So you can spot an issue right away. The drone doesn't even have to land. You can know that there's an issue with that antenna straight away based on the live feedback that you're getting. And so and that's radiated power. So it's measuring effective radiated power. The whole system is all calibrated antennas, receivers, and antenna cables. Okay, next slide. All right, then just to finish up on my first section. So you've got all those antenna patterns you've just measured, right? You've got the radiated power, you've got the elevation pattern, and you've got the azimuth pattern. You've got the measured data. Now you can take that measured data and through our software, export that in a format that is now you're able to now import into ATDI's coverage measurement software and then create the predictions based on the measured data, the real data, and not necessarily the designed data that it hasn't been proven yet. And that about takes me at the end of my part one. Yeah, if you want to come back. Yep. Good. Thank you.
Thank you, Jason. All right, guys. So again, I'm Yaya for those who just joined in now. So Jason showed you how you can use drones to actually model the actual antenna pattern. Okay, so it can be used for validation, also can be used to improve your model. So what I'm going to show you now, I'm going to show you what do you do with this after that. Obviously, the drone cannot fly everywhere, but prediction can be done everywhere. So we're going to use the measurements as the feedback and then construct 3D modeling in a software environment and then do the predictions to do further analysis and produce plots and heat maps. So for me to do this, I need to use GIS layers. So we're talking about terrain, clutter, buildings, vegetations, urban, suburban. So we're going to reconstruct the RF environment and apply rules of physics, deterministic propagation model. So propagation model is a theory you apply to emulate signal behavior as it travels through the environment. So signal hit the building, it diffracts. There will be reflections, there will be outdoor to indoor penetration, there will be line of sight, there will be not shadowing. So all this stuff, we can predict them using a propagation model. That propagation model later on in the second session will show you how I can tune the propagation model as well using the measurements. Then I'm going to move on to the requirement. So what Sixarms is doing give us a challenge, because if flying the drone vertically and he can capture 0.1 degree, even more precision. Okay, so traditionally antennas are modeled with 1 degree stepping. So each 1 degree you sample the polar graph, but he can do 0.1. So that requires us as well as a modeling tool to support the 0.1 degree. And this is very important because not every tool in the market can handle 0.1 degree precision. Then I will just touch quickly on the link budget, move on to digital TV coverage, do population analysis for you, establish how many people you can actually reach out to using a transmitter. And then we close this session by doing correlation between what he measures around the site and what the tool predicts. Okay. So first, let's start with the GIS. This is an example of digital terrain model. I'm going to show you a live one as well. I've got the software handy. So this is the digital terrain model. And you can see each pixel is equivalent to X by X meters. So when I say 20 by 20 meters in the software, each pixel in the software is a 20 by 20 meter. This is medium res. We call it medium res. There's also high res. High res means every pixel on the ground is equal to 2 by 2 meters. So every 2 by 2 meters on the ground, it becomes pixel in the software. That give you outlandish accuracy, especially if you're doing gap fillers. If you're designing gap fillers in the city, You can model the high-rise buildings, and you can establish confidently what the coverage look like. So this is, guys, the environment I'm talking about. This is a clutter. So look at the orange and the blue and the brown. These are different environments, like urban, suburban, rural, okay? As you go away from the city, the buildings become a bit lower, correct? So that means they will exhibit different impact on RF propagations. So in the software, I can distinguish high-rise from urban, from suburban, from rural, from forest, and I can define different RF characteristics, different elevation. So that give you really a great accuracy. You can't just do modeling in TV with a bare terrain or empirical model in Excel spreadsheet. You need to have this sophisticated RF planning tools. This is what high-res 2 meter look like. So you see in the previous slide, it's a block of buildings or a class for the area. Now this is a high-res. This is a 3D representation. You can even capture like a cluster of trees as a model. So the trees, the building footprints, the water, the streets, all of these can be captured. And then that's what you have in the end. You have a 3D environment where you can deploy the tower on the rooftop if you want, or on a skyrise, and you can do the RF predictions. You can also do the EME emissions. You can check if you're causing violation to the EME levels for any of the nearby buildings as well. So this is, guys, usually have a vertical 0.5 meters precision. So the vertical precision is about 0.5 meters. And we use satellite technologies in order to produce this kind of maps. So guys, when I say deterministic model, this is extremely important because that's how you can achieve the accuracy. Deterministic model is a model that used the feedback from the terrain. It used your definition of a height. Who's receiving, a person or a car or a rooftop? Okay, so each one of these receivers have different height, and different height would produce different prediction output. So look at the plot here on the top right plot. Let me activate that marker. Laser, here you go. So guys, you see this one here? This is coverage heat map for digital TV, but based on the receiver 1.5 meter. This is 1.5 meter receiver. Here in the bottom, we change the receiver height to 10 meter. You see there's more coverage. It appears to be there's more coverage, okay? So this propagation model is smart. It will adapt based on what you define as input parameters. For example, receiver height. This is what we call deterministic, okay? So the terrain become, when you, for example, flying high, the terrain becomes less relevant. There's no more obstruction from terrain or from clutter. So the tool has to adapt. And that's also beneficial for the verification of drones, because drones can fly vertically as well. So here I'm taking a case by case. So you see, this is a transmitter in the middle, and I'm evaluating signal for that location. Now that location is located in a hilly environment. So you see that this is a vertical view here. This is a signal behavior from the base station to the receiver here. And you can see there's mountains in the way. These mountains, you can see them here in the top view, and you can see them here in the side view. So that location naturally would receive weak signal. Now, if you compare it now to this guy here, this guy is in a valley, and then he got a really nice line of sight from the base station to the receiver. So you expect to have here improvement in the coverage. And that's reflected here in the second profile here. So the base station is on the left, and you see this nice line of sight to that receiver position. So guys, these propagation models, they can really predict the impact of obstacles. Like there's a building here. You see we've got penetration. We've got first free space from here to here, free space. Then when the signal is hitting that building, is diffracting, shadowing. And then when it's going inside the second building, you've got penetration loss to penetrate the building. That's a penetration loss. And then depending where is the receiver inside the room, you would undergo absorption loss. This is a very sophisticated model that can predict outdoor and indoor. It can consider the impact of the building you're living in and the buildings that are in the way from the transmitter to the receiver. Okay, so this is, guys, what we call the deterministic propagation model, and then that allows us to model the Fresnel zone. We can model the lateral diffractions. We can model multipath, and we can take the impact of multiple obstruction environments by looking at the diffraction theory, looking at the reflection theory, and defining also outdoor to indoor penetrations. So back to the 0.1 degree precision or vertical measurements. So guys, this is what's happening. So the drone is flying. Probably you saw in the video, it's going around. It chooses a face. It chooses one side, and then he starts flying down, up and down, okay? Because he wants to sample the main lobe for that face. So the tower has 4 faces, okay? Let's say it's Omni. It got 4 faces. Each face, you've got maybe 8 bays. So what he's going 45 degrees roughly, for example, or 90 degrees, and then flying up and down to sample the bay or that face, to sample that face. Then he's going to the second face, and he's doing that. That's why he's doing that 4 times. So each time, guys, you need to capture enough measurements to establish the vertical pattern. The vertical pattern. This is extremely important, the vertical pattern, because that will help you understand if you are focusing your beam or coverage to the terrestrial receivers, not to the sky, okay? So what we do is that we need to capture this 0.1 degree precision and capture it in a matrix. So we have a matrix CSV file that we use for that purpose. So let me show you. So I need to share my screen again. So I'm going to share this screen. There you go. So it's okay on the screen? All right, so let's have a look. So guys, this is the antenna. Sorry, the antenna. Here you go. This is the antenna. So this is the antenna pattern, 3D antenna pattern, 3D, not 2D. So 3D means you've got the full 360 measurements, okay? And then you've got from like minus let's say 10 degrees to positive, or depending on the direction, from positive 10 to, for example, minus 10. So you can see here the angles from minus 90 all the way to plus 90. And the stepping is 0.1 degree. This is the vertical axis. This is the vertical axis. And then you've got here from 0 until 359. This is the horizontal axis. So this is the antenna pattern. It's a 2-dimension matrix. And then in each value here correspond to specific azimuths, specific elevation or depression angle. And then here we define the dB discrimination, which are measured. So this model, guys, now can be easily captured in a software. So in a software, we just have to do capture the antenna here. So this is the antenna pattern that we use in the modeling. You can go and choose, for example, a 3D antenna pattern, and then you can easily go and load it. You can load the antenna like this, 3D pattern. Okay, so this model will be used in the modeling and simulation. Now, I wanted to talk just quickly about link budget. So this is, guys, the RF environment. This is the RF environment. So I'm going to take this example in the Philippines as a use case. This is the example of the environment I'm going to use for the modeling. So you can see the terrain, and you can see here we have the clutter. So this is the clutter, guys, the urban, suburban, rural, the roads. This is the RF environment. And we can emulate this. Let me just move this out of the way. All right, so share screen, profile. So profile. So you can analyze from that tower to any position in the country, put the receiver height, say 1.5, and then you can establish the propagation criteria from the base station on the far left to the receiver on the far right. And you can see these fluctuations at the green, these fluctuations in the signal correspond to the effect of the RF environment on the reception. So now move on to this. So the link budget. So guys, link budget, this is also one of the most important step in RF modeling. So very often I hear there is ITU standard, and then there is the local standard, which is completely different. So the ITU standard, for example, based on European countries, where everybody have a nice rooftop antenna oriented properly to the right base stations, okay? And then you've got professional installation, cables, and so on, down to the TV. Or if you're talking about digital TV, also same story. So what we usually do for clients in each country, we re-establish what is the minimum field strength that you need to define or establish a coverage. For example, it could be in Europe, for example, the minimum field strength 50 dBu, could be somewhere else 60, 65 dB microvolt per meter as a criteria. So you need to do a link budget. So this is here just a spreadsheet just to show you what considerations you have in place. So you need to start, guys, by considering, for example, the cross-polarization loss. Not everybody have ideal receiving antenna. Not everybody have nice cross-polar antenna that can capture both powers, E-planes and V-planes, and then combine the two. So here you can make different judgments, change your criteria in order to establish more accurate understanding or interpretation of what coverage is. So you can define the cross-polarization discriminations. You can define the building penetration loss. For example, if you're expecting your audience to receive signal inside the room, inside the house, not on the rooftop. You've got rabbit antennas, for example, installed and connected to the TV. That's another challenge. So you need to take into account the outdoor to indoor penetration effect for these buildings. So you can define these parameters here. You can see we're making here an assumption, for example. We've got the standard deviation, the entry loss 7.5 dB. You've got here the derivations, and then you establish also your confidence level. You see here we end up designing, for example, for rooftop, we design for 56 dB microvolt per meter, whereas if you want to receive inside the house, you need to over design and then target 73 dB microvolt per meter. So I don't intend, guys, to walk you through these entire parameters, but what I want you to understand here is that depending where is the receiver, where is your definition of a receiver, the design criteria, it can vary considerably. And then instead of having coverage like this, you end up with a coverage like that, okay? Because of all these factors like antenna pattern, antenna discriminations, antenna gains, cabling losses, and also outdoor to indoor penetrations. So now I'll talk about the coverage quickly, and the population analysis. So this is the tower that I picked up. So this is the tower. So let me hide this path for now. So this is the tower, and I'm going to display the map, satellite maps for now. This is a satellite map. How can I get rid of this? Okay, so this is the transmitter. And now what I can do, I can calculate the coverage for this transmitter. So this is what the reception look like. So here is the heat map. So that heat map, for example, I can start with something like 63 dBu, and then let's say 73 dBu, and then 83 dBu, and then 93 dBu. So you can represent this is different color palette, and then establish what the coverage look like. So this is the coverage based on an antenna pattern. The antenna pattern can be, like I said, the loaded pattern from Sixarms. So if you want to calculate the coverage at different elevations or different height, you can just simply here define the receiver height, example 1.5, and then distance, let's go do it for 50 kilometers. So this is the prediction process. The software is sending a guide to each pixel in the map, and then establishing the profile, running the field strengths predictions, and then identify or establish the signal level at that spot. And that's translated to heat map like this. Now, if I want to do the population analysis, I want to see how many people actually can receive a signal of, say, 63 dBu and higher. So this is the map, this is the tower, and then I want to know how many people living in their area and actually receiving a signal can watch the program. So very simple, guys. You go to the report, and then go to the raster, and then raster file coverage. Now, before I do that, I want to show you what the population heat map look like. So we use the official government source to model the census data. I really want to get rid of this. How can I get rid of it? So guys, this is the raster for the population. This is Philippines, this is Manila. So you see, here, hot. Hot means lots of people living there. And here we are defining how many people living in square kilometer, for example. So if the step here resolution is one square kilometer, I think it's 100 meters as well. Let me double check that. Yeah, the resolution is 40 meters actually. So each one of these dot is number of people living in a 40 by 40 meter area. Okay, that's how granular it is. So here hot means lots of people living here. So it's getting colder and colder. That means less population is living as you go away from the city. So this information, we're going to overlay them here, and we're going to correlate the coverage with the population based on minimum signal level, 63 dB microvolt per meter. So remember, this number comes from the link budget. So if you're going to target 73 indoor people, it's going to change the game. It's going to change the number of people you can reach. Okay, so this is the number, very easy. So I can see, guys, we're covering roughly 65% of the population in the map. So this tower covering 65% of the population in that map. And you can see here the number. So this is 1,000, and then it's 24 million. 24 million in the Metro Manila and the new area. That's how many people this base station is covering. So I think it's now the last point. So what we're going to do now, so I'm going to use the measurements that Sixarms produce. So Sixarms, that's what they're doing, right? So they're flying the drone around the tower and then going vertically.
5 minute warning, yeah.
How much time, sorry?
Yeah, this is your 5 minute warning.
All right, cool, 5 minutes, should be okay. So guys, here I'm defining sample points around the tower, near the tower, not too far, okay? So I'm gonna use the measurements that passed down to us in this example. So here we have antenna measurements. So I'll show you the format, guys. So format is very simple. Position, longitude, latitude, antenna height, which is the drone height in that case, the measured value, and the coordinate system, okay? So this is dB microvolt per meter. This is meter, and this is the lat and long, and then the point name. So I'm going to use this information, guys, very quickly to do a correlation. And it's fully automated, really. All you have to do is to draw a polygon around here, and then you go to point-to-point correlation. And we pass the measurements, and we hit OK. That's going to give you a very quick report. Each point, what is the measured value? And what is the simulated value? So we're doing comparison, measurements and prediction. And I can do this based on the old antenna or what do you call it? the estimated antenna from the vendor, because the vendor, they give you estimate, and the estimate is based on free space, and it's not based on the tower structure itself. So they give you a model, a mathematical model. They give you a nice pattern. And this is the emulated one, or the estimated one. And then we could use also the measured antenna to do the comparison and then establish the error margin. So here we are comparing what was predicted versus what was measured or simulated. Sorry. And then here you can see the measured value is 115.8. Here is 118.87. So the delta is 3 dB. And then you can see in the end the correlation within 6 dB. And you can also establish the actual average error. Just click on the list, and that's going to produce for you the stats. And this is the delta. Highlight them. And you see, guys, the average is 0.54 dB. That's algebraic average. 0.5 dB discrepancy between what we're predicting and what we're measuring. The reason we use near the antenna, because this is where you have line of sight. And line of sight is important in their case. So now I'll pass on to back to Jason.
Okay, we'll work with that. So ATDI HDZ has now given us a great coverage prediction based on real measured antenna patterns. What do we do with that? Just flick over. So there's our coverage field strength. Quick recap. What's it all about? You know, where does my signal go? It's a prediction based on algorithms, and you can either use the designed pattern from the manufacturers, or you can use the measured patterns and rated power from the Sixarms system. What we want to try and achieve in this next section, though, is a little bit different to what you'd normally try and achieve with a field measurement. So traditionally, field measurements, you would go out and deploy a system and go do some measurements to determine whether your antenna is working correctly. What we're doing with our coverage field measurements is we know how our antenna is working because we've just done the antenna pattern measurements with the drone. What we want to do is we want to test whether the ATDI HDZ coverage modeling values are close to what our measured values are. So we're now testing the propagation algorithm as opposed to testing for the antenna. Now this shows, there's a great picture here of, I'm not going to say the old way of doing things, but it's the traditional way of doing things with a very expensive setup on the right-hand side with your coverage van and your 10-meter pump-up mast. And, if you had nothing else except that tool, that would be a great tool to at least get some coverage measurements. However, we do have new tools, and the deployment of the drone to gather that data is now an automated process. And the good news is that, you can put the drone in the back of a rental vehicle. You don't have to drive your vehicle across the country, your big coverage van. Everything is now a little bit simpler logistically. Now, there's a couple of procedures which, a broadcaster or an infrastructure owner can do right now in terms of testing. They can be proactive, right? So you install a new antenna system, or you want to check your antenna system, you'll send out the vehicle and you'll go do some measurements to try and determine whether the coverage is what it is what you expect. And what you expect is what you've just created in the ATDI, the HDZ coverage prediction. The second thing you can do is deploy a drone-based system and go do the same thing. Or you can do what a lot of people do, and that's just ignore it. Don't go and test your antenna system. Be reactive. Rather wait for people to complain that they're not getting a signal. Whichever, I prefer the proactive testing approach as opposed to being reactive. So what does the drone offer in terms of over the coverage van? Well, this picture is showing you a few things. What it's showing you on the scale on the left-hand side is altitude. So for one thing, we can fly the drone from the ground level to 100 meters, to 200 meters, or to 50 meters, whatever you prefer. The point there is that the traditional way is that blue line. So that blue line you can see there is basically the limit of a 10-meter coverage van. And so what you're getting from data, the X scale there is field strength. So as the drone flies from ground level into 30 meters, you're getting a lot of multipath close to the ground. So obviously your signal's getting hit around by buildings or whatever the local clutter is. And then at 10 meters, as you increase your height to 30 meters, you can see a nice gradual increase in field strength. Now that field strength will increase until what you get to is free space path loss conditions where the clutter and the multipath are not affecting your measurement reading. So that gives you a more solid point of reference. So the 10-meter measurements, they're not anything new. They're based on RTU or FCC guidelines. However, now with the drone, we can get a lot more data. And we gather as much data as we can because in this day and age, data is king. So we can use that data, and we can use that data to help compare against and improve prediction algorithms, clutter loss, and optimized diffraction models. This allows us to collect a lot of data in very little time, for mass automation and coverage validation tasks. This slide is basically just a nice visualization. So what are the technique you use to measure your 10-meter coverage? You can fly up 10 meters, fly forward 30 meters. That's one technique that they use. The other one is they use 5 points, where you create 5 points that are 30 meters apart and fly up 10 meters. Whatever tool you use, the drone can automate that process. So it's basically a one push button, and you'll get your signal strength, and you'll get your cutted signal strength by making use of some nice visualization tools. Okay, but the crux of what we're trying to achieve here is this plot here. We've got a coverage prediction from Yaya and ATDI. What we want to do is validate that coverage prediction. We don't want to validate the antenna. We want to validate the coverage prediction. So all we need to do is choose a random amount of points. Now, we don't care where these points are, because what we're testing against is we're testing against the coverage model and its ability to give us predictions that are close to measured values. So we can have non-line of sight values, we can have line of sight values. We're in the coverage area. So we randomly choose, 10 to 15 points based on a 100-kilometer kind of coverage. And we'll take the drone and we'll fly it from 0 meters to 30 meters, and we'll collect all that data. We can then visualize that data, I guess, which is what this slide is showing you. And if you had to zoom in, you would see that point number 16 there is, it's got an arrow, and that arrow is colored according to its measured field strength. And you can see that the predicted and the measured are relatively close. And if you click on that, you can get your measured field strength at different heights. To better explain that though is this next slide will probably make a bit more sense. So we chose 15 test points, and remember we're confirming we're validating the coverage model. We're not validating the antenna anymore. We've done that. We determine whether those, with the help of ATDI, we determine whether those latitude and longitudes are line of sight or not. We work out, we automatically calculate the distance, the depression angle, the azimuth to the transmit tower. And now we've automatically thrown in ATDI's predictions here. The prediction at 9 meters, this one's a USA job, so it was 9 meters, we did this one. And we do a prediction at 25 meters. We then also automatically populate the rest of the column with measured data at 2 meters, 5 meters, 9 meters, 15 meters, 20 meters, and 25 meters. That's all there for reference, although we don't use it in any of the calculations. We're just collecting all that data. But the really fun statistic here is that last line. And we use ATDI's correlation function to give us a correlation between what we measure and what it's predicted for us. And we do an average of that. So we can see that the correlation for this particular data set is 96.7%, which means that that tells you that tells you, gives you confidence that the prediction model that's been used in the clutter and the digital terrain is all very valid for this particular location and this particular data set. Because you're measured, for example, 81.5 dB microvolts, and you're predicted 81.5 dB microvolts. Another one, 72.2 dB microvolts versus predicted 73.9. These are really close. This gives you some genuine confidence that that prediction is doing its job, which means when you go back to the full coverage location, you've only measured 15 points, but that's all you need to measure, because now you have a really high confidence that that prediction is doing what it should be doing. So you can then believe when it says that you've got 44 or 41 dB microvolts out here near the ocean, that's pretty much what you're going to have, because everything's been proven. And I'm going to finish the part about predictions based on the correlation there. And this data, which we've been gathering all here, is going to eventually be used to help tune clutter loss and propagation models. And I think Yaya might talk a little bit more about that process.
It's interesting. So what we're going to talk about now is how we can compare measurements to prediction in a statistical way, and then establish the error margin, and then tune the model. So tuning the model means we blame the GIS. We blame the GIS. So if the measurements say something, predictions say something else, say, all right, maybe something wrong with the RF environment, the building heights or the clutter heights. Let's go tune the clutter. Let's go tune the propagation model to lock in and then establish the accuracy. Because at the end of the day, you want a heat map, a global heat map, show you confidently what the coverage look like. So for me to do that, I'm going to do it in HTZ. So guys, this is the software. So out of the box, this is untuned. Out of the box, we got this model. We've got this coverage. The question is this correct? So somebody did measurements in this example. So close. That's the drive path. Okay, the red. So you see going here around the side. Why we go around? We go around because we want to sample the antenna from different angles, and we go around. You need to have a nice route, and the idea is to sample as much measurements as you can in different environments: urban, suburban, rural, and so on. So I want to compare the measurements done here with the prediction done by the software. It's extremely simple. I will show you the measurement file that I have. So here we have drive test. I'll open the drive test for you, and I'll show you what it looked like. Extremely simple. This is the long, this is the lat, this is the signal level, and this is the base station you are measuring. Because you might be doing multiple base stations at once. You could be doing multiple frequency measurements at once. But that's how simple it is. And guys, look at this spreadsheet. There is about here 2,145 samples. So 2,145 measurements. So these measurements, I'm going to use them as a feedback to the tool to do first correlation. So to do correlation, it's extremely simple. You go to measurements, correlation, generic XYE, long, lat, and field strength. And guys, regardless what vendor or what drive test tool you have, they can all export the measurements in ASCII format, Excel or CSV. So we run the function, we feed the measurements, drive test, okay? And that's pretty much it. So this is good to go. You hit okay. And now we have comparison. I'm gonna zoom in. So what are you looking at now? The yellow graph is what you measured. The green graph is what you predicted. It's not coming up?
It is now. It is now.
I think when I
it was just a bit delayed.
This one is annoying. I don't know how to get rid of this. So is it still now?
No, yeah, I can see. So good.
Is okay? All right.
Yeah, correlations there.
Yeah. So guys, you see there is measurements, which is noisy, and there's a green line, which is what you predicted. So if I click on a specific point, I can see the delta here. So measured is 99, predicted 92. All right. And what is really important here is the stats. Look at the stats. 82% of the measurements are within 6 dB bracket from the prediction. 82%. The standard deviation is 4%. This is the distribution. So we have on average 2.6 dB error, and we are pessimistic generally. Minus means pessimistic. Okay. This is, if you take this to any software in the industry, we say this is excellent already. Don't waste your time. Don't do more. Out of the box, this is providing excellent accuracy. But I'm not satisfied. I'm going to do model tuning. I'm going to show you how we can improve this even further. Okay. So this is, guys, the statistical analysis to establish the confidence. So look at the correlation, 91%. We have 91% correlation, agreement in the trend. When prediction goes down, measurement goes down. When prediction goes up, measurement goes up. There's agreement, almost 91% agreement in the pattern. Okay, so usually I target 98%. And you can see here the standard deviation is 4 dB. Usually I target 3.4, 3.5 dB as a target. This is already excellent, but I want to show you how we can tune. So how do we tune this? How do we tune this, guys? The tuning is done by understanding the RF environment. So here we have the light blue here is urban. This is urban area. You see this light blue is urban area. This dark blue here is suburban area. I'm reading here. So urban, suburban. Remember that. We need to tune urban, suburban. And also that green one is dense urban. I'm going to tune these 3 clusters. So to do the tuning, guys, you go to the measurements, and then you go to tuning. So it's also fully automated. If you want to tune the model, you just go like this, tune clutter. And I'm going to target what I said. I'm going to target suburban.
The menus, yeah.
Sorry?
I can't see the menus.
All right, stop sharing. And I'm going to share again. And I'm going to share this and confirm it's okay. So this is suburban, urban, and dense urban. I want to tune these 3 clusters because that's what I did my measurement. I haven't done measurements in the rural area. Don't try to tune it. So we're just going to tune these. And we're going to tune them by applying a factor from 0.4 till 0.8. So I'm going to try 0.4, 0.5, 0.6, 0.7, 0.8 with stepping of 0.1, and then you run it. That can take a minute. So what the tool is doing now, the tool is changing the environment and running prediction again and doing comparison. So it's going to establish a benchmark where we can select the optimum parameters from that tuning exercise. And end up, we're going to have with correction factors per cluster, suburban, urban, and dense urban. And remember, previously we had 4 dB standard deviation. We had 91% correlation, and we have about 82%, I think, within 6 dB. So we're going to do it again and then see how the accuracy would improve. Done. So look, guys, Clara code 2, which is probably urban, 2222 is done 1, 2, 3, 4 times. And each time the software is changing a little bit the factor from 0.4 to 0.5 to 0.6 to 0.7. And you can see here the percentage, how it is improving. Okay, so let me go back. Close. So now look what happened. The software has changed the environment for the urban, suburban, rural. So it changed the diffraction factor to 0.4. Okay. So now I can do the prediction now one more time. Coverage prediction based on 1.5 meter, I think the height was wrong. 50 kilometer. So I'm doing the prediction with the new environment settings, with the new tuned model. Now we do the correlation. One more time, comparison. Bingo. So guys, look, we have now 95% of the measurement within 6 dB. It was 82%. Now we have standard deviation improved from 4 dB, which was already excellent, now to 2.57 dB. So
just having issues, we're unable to see it on the Zoom.
Yeah, I don't know what's the problem with the Zoom.
Yeah, I think there's just some lag on the Zoom.
Yeah, that's all right. So guys, so this is now improved to 2.57. This is the most important KPI in correlation. Now followed by the average error 0.09 dB. So on average, you are not wrong in your predictions. And now you see here improved from 91%, the correlation factor or the confidence, to 97%. So this is, guys, how it works. The measurements captured and used to compare with prediction out of the box. If we don't like it, we can tune the RF environment to increase the confidence. And now we have the heat map. That heat map now is improved accuracy or improved confidence in it by from 91% to 97%. So I think it's done for the time, right? So we still have some time.
Yes, there's still 5 minutes left before Q&A.
Let me also just touch quickly on a small topic, antenna modeling. So guys, this is how vendors really give you antenna pattern, the polar graphs. They use antenna simulators. Okay, so something like this. So this is what they do. So they can model the tower and they can put these different faces, okay? And then they use antenna theory in order to emulate or establish the antenna pattern. So they can establish something like this. For example, put the frequency of simulation, and then they can produce antenna radiation pattern, just like that, okay? Now this is correct, assuming the installation is perfect and done like in free space, okay? Assuming it's perfect, you will get what you emulate. But as Jason was showing, this doesn't always work like that. There's always a human error. There's some manufacturing impurities that can produce different pattern than what you expect. And that pattern means it might be steering the power in the wrong direction, not to the intended audience. So they can do the pattern calculations. This is the horizontal pattern on the left, and this is the vertical pattern on the right. And you can produce a heat map to understand the emissions. So for example, if you have concern about EME, human exposure to emissions, and you can also establish this heat map, and then you can understand what the signal look like. This is the side, this is the horizontal one, and this is the vertical one. So what the drone is trying to do, the drone is trying to fly, and then is sample this signal and understand what the radiation look like. Okay, so this is, guys, based on antenna theory and prediction done in a tool. So I think this is it, guys, for me. We want to give time to questions. So if you guys have any questions, Jason from Sixarms and then me are here to assist you guys. Is there any question from the audience? Or from online, John, if anybody. By the way, guys, the webinar is also being broadcasted, the workshop broadcasted online to audience.
Yes, yeah, there's a couple questions from some online participants. Let me know when you guys are ready to field them.
I'll check the audience here. Did you want to?
Yep. Okay. A question here from Guillermo. And I'm just going to read it out loud so that the audience can hear it, listen as well. So in 50 kilowatt broadcasting stations, what type of drone would be used? So that's a good question. And, you know, in the beginning, we were pretty skeptical about, you know, EMI susceptibility of the drone itself. And so in the early days, we did use some heavily shielded drones, which we had to manufacture ourselves. But luckily enough, in this day and age, there's a couple of brands that you could use that are off the shelf that will quite happily sit in front of a 50 kilowatt antenna system, you know, obviously depending on the gain of that antenna and the frequency. We do generally find that FM radio likes to bounce off lots of things and likes to penetrate electronics. So FM radio, we do have a lower threshold. 50 kilowatts though is no problem. For FM, we're measuring, you know, at the moment, you know, we can measure a 500 kilowatt FM antenna system with a you know, standard off the shelf drone with our Sixarms equipment on it. I guess if you're using your own drone, I'll just be really cautious as to, you know, what could get affected, which is generally the GPS system and the compass. So hopefully, Guillermo, that answers the question about what drone we use, and you know, without being specific about manufacturers, there's a couple out there. You know, the standard decent drone that can carry 1.2 kilograms for about 25 minutes will probably be fine. We're also, just to clarify the point there, is we're actually measuring in the far field, right? So we're not trying to fly 1-2 meters away from this antenna system. We're trying to fly in an area that, you know, the beam or the panels have all formed, so the radiation patterns it's been fully formed. So that's as close to as practical we'll fly in the far field. Far field is an equation based on the length of the antenna and the frequency. This is the second question there. So Guillermo, I hope that one answers that. Second question, Guillermo, tower measurement points close to the radiating system. Tower, an isolated monopole or a tower folded?
It's more of just a comment.
There are electric fields, magnetic fields, yep. Yep, no, just anyway, your comment there was that you've got to be really careful about flying really close to radiating fields because there are electronics that get exposed. And, you know, you don't really want to be flying if you don't have to be. We do always try and fly at a certain distance to protect all our equipment. And we actually add a lot of high power attenuation to protect all our spectrum analyzer components. Flicking through, John, were there any other questions that you saw?
Yeah, there's I think one that might be for Yaya, but we'll skip that one for now. There's one for you, Jason. Can the drones test be used for cellular mobile coverage point of view? Yep.
So the short answer is yes. We are using drones in the cellular testing environment at the moment. You just need to realize that when we're measuring, say, you know, DVB-T, our receiver is measuring different parameters than when you're going to be measuring cellular. So we actually have a different receiver we use for cellular antenna pattern measurements, as well as we can do cellular coverage. So yeah, the drones can be used in that situation.
And I think the last question we have here is just about the section on the model tuning. Last section. What was the model, the propagation model that he used?
Yep.
before the actual model tuning.
I'll hand over to Yaya.
Thank you.
Question about propagation model, right? So
yes, that's right.
Well, one of the questions was what propagation model we used to produce simulation. So I used Dago 94 diffraction theory, which is ATDI proprietary. And what it does, it takes multiple knife edge. It doesn't just use 1 or 2 or 3. So it's a recursive approach to taking multiple knife edge for the diffraction. And it does produce really great accuracy when it comes to diffraction. I also used the coarse integration. Coarse integration, which means it takes the average height of the clutters crossed by the signal as a corrective term on the top of free space. So free space plus diffraction plus coarse integration. That's the propagation model I used. And if I ask one question to Jason, so Jason, did you establish any percentage of what is the chance of having wrong antenna pattern or incorrect antenna pattern, like when the comparison? Is it 20%, 30% of the time?
Yeah, no, that's a good question. So look, you're only ever going to get a very small amount of percentages of the antenna being 100% perfect, right? You're going to get slight variations here and there, which is generally you can live with them. They're not going to deter on your coverage prediction, your coverage estimate. Now, in terms of putting a number, it's quite difficult. So I can probably say in every 10 antennas that we measure, 2 to 3 antennas have issues, right? So that doesn't matter whether it's an FM antenna or whether it's a UHF antenna. And generally, we found that the issues are normally installation related in terms of pointing the antenna in the wrong direction, misaligning the mounting bolts, putting an antenna on as a side mount antenna without realizing what the effects of your radiation pattern are going to be. So yeah, 20 to 30% of antennas we measure have some sort of artifact that needs addressing.
That's quite a high percentage.
Yeah, that's quite high.
Yeah, that means every commissioning, there should be some testing after that.
Yeah, we prefer to encourage proactive testing, but I guess, you can take that third approach, which I showed you, which is, don't do anything until you get complaints, but I'm not sure that's a good business model to be following.
And Jason, over
no,
time,
probably not long term.
When does the antenna start to degrade over time? Let's say they commissioned it today, it was perfect, working nicely. Do you encourage a visit every 2 years, every 4 years, every 5 years?
Yeah, that's also a difficult one, and that depends on the company, I guess, who owns that infrastructure. If they have a nice routine management plan where they're visibly inspecting antennas and testing them, every 6 months, every 12 months, you probably don't need to do an antenna pattern all that regularly. But if you kind of leave antennas lying around with being weathered and going through cyclonic events without checking them, once every 2 years or so, I'd say that you're probably going to find that you'll have a few antennas which won't be doing what they should be doing.
Yeah, that actually leads to a question that I had, was about extreme weather events. A lot of these, especially in the typhoon regions where the antennas could be affected by extreme weather events. Do you often see that when you're out doing your measurements?
Yeah, look, water getting into, so it's a severe thunderstorm, you're going to get water, potentially going to get water ingress. So you get water into your coax, into your cables, you get water into your dipoles, that's going to, potentially you won't notice, that's going to degrade your performance. Potentially you won't notice the 1 or 2 dipoles you've got, that are out of existence if you've got a 24 dipole antenna. But over time, that dipole is going to rust and just, drop off. We've come across a couple in Australia, which, dipoles are missing because they've been hit by ice or, they've just rusted off.
Yeah. All right. Thank you, John. I think we conclude for
now. Thank you.
We finished here.
Yes, I think so too.
All right. Thank you, everyone, for your time.
Okay. You guys going to shut off on your end?
Yes.
Okay.
Thank you.
I'll take this chance to thank Jason and Yaya. Thank you, everyone, for joining today. You will have access to, you will already likely have contacts for one of us. Feel free to reach out.